right, guys, so we're going to keep going. And one thing that we're going to deal with acids and bases is the common ion effect. And if we're looking at something like acetic acid or vinegar, the overall reaction for that is the acetic acid in water produces the acetate ions and hydronium ions. And we could use the Ka and figure out the pH of this to be approximately 2.87. Now, this goes and ties back into equilibrium. But looking at what would happen to the pH if we were to add sodium acetate to this. So if we did that, it would add acetate ions, which is on the product side. Which if we add products, that means equilibrium shifts to the opposite side. So it would shift towards the left, towards the reactant side. Meaning that there's less products that are going to be produced. So less hydronium ions. Which means that the pH would increase. If there's less of those hydronium ions, it would make it go more neutral or more basic versus more acidic. And you can kind of see that here. The picture on the left, we just have acetic acid, which is that pH of about 2.9. Whereas on the right, we have the acetic acid with the sodium acetate, which is going to have a pH of about 4.7. So it's going to reduce the amount of hydrogen ions, increasing the pH. So let's look at if we wanted to compare these. So let's look at what is the pH of a 0.3 molar HCOOH solution. And then we want to know what is the pH of the solution if we have that acid and 0.52 molar KCOOH. So let's address the first problem. So if we wanted to find the pH of the 0.3 molar HCOOH solution, this is a weak acid. So remember, we have our overall equation of the acid in water produces the hydronium ions and that anion. We have 0.3 molar that we're starting with and none of the ions initially, which means we have to increase on our product side, decrease on our reactant side. And then we can use the Ka of that acid, which is 1.8 times 10 to the fourth. We can solve for X, which is our hydrogen ion concentration, which we can use to determine pH. So the pH of this acid would be about 2.13. Now, if we have our acid with our original, or with the salt, with the KCOOH, what that does is we're still starting with the 0.3 molar of the acid, but we're also starting with 0.52 molar COOH. So we have both a reactant and a product at the beginning. Now, since we don't have any of the hydrogen ion or hydronium ion, we still cannot subtract on our product side, so we have to add on our product side. So there's our equilibrium values, and using that same Ka value, the 1.8 times 10 to the fourth, we can essentially ignore X for both of these. It's 3 places different, so we can ignore X. Plugging in those values, we get that X here is 1.0 times 10 to the fourth, which is a lower concentration. And the pH here would be about 3.98 overall. So you can solve these with ice tables overall to solve them. That's kind of what we've done before. There is another way that you can look at these. And this is our Henderson-Hasselbalch equation, or you might see this abbreviated as HH equation. So you can use this whenever you have a solution that has amounts of the acid and its base pair. So if you have the acid and its conjugate base, or a base and its conjugate acid, you can use this. So remember, here's our kind of basic acid-base equation, or acid equation, where we have our acid and water makes the hydronium and our conjugate base, that anion. Henderson-Hasselbalch equation is actually on your reference sheet. I'm going to show you kind of how we derive it. So this is the Henderson-Hasselbalch equation that's on your reference sheet. It tells us that the pH of a solution is going to be equal to the pKa of the acid plus the log of the base over the acid. How we got that, it all started from Ka. So they kind of took Ka and solved for the hydrogen ion because we need that for pH. So that means that Ka times the acid concentration over the conjugate base. They then, to get pH, they have to do the negative log. So they did negative log of both sides. And then it ends up simplifying to what we have as the Henderson-Hasselbalch equation. And where we can ignore X when X is so small approximation is kind of implied in the Henderson-Hasselbalch equation. So this will save us a little bit of time when we have both our acid and our base amount overall. So let's look back at the problem we just had, but we're going to solve it using the Henderson-Hasselbalch equation. So we should get about the same pH. It might be off by a decimal point or two, but it should be pretty close. So it wants to know the pH of a solution with 0.3 molar of our acid and 0.52 molar KCOOH. So remember, the COOH is our conjugate base. So our Henderson-Hasselbalch equation, we're going to have the pKa of our acid plus the log of the base concentration, that conjugate base, over our acid concentration. When you plug this in the calculator, and I want you to be careful because whenever you hit the negative log of Ka, it will open parentheses. Make sure that you close those parentheses before you continue typing in the rest of the equation. So this will still end up with a pH equal to 3.98. So let's look at another one. Here, we want to know what is the pH of a solution of 0.12 molar lactic acid and 0.1 molar sodium lactate. And it tells us the Ka for lactic acid is 1.4 times 10 to the negative fourth. So we're solving for pH. So remember, pH is equal to pKa, so negative log of Ka plus the log of the base, which would be the lactate ion, over the acid, the lactic acid. And like I said, you're going to put this in the calculator, but make sure that you close parentheses after you open a log. And we're going to end up with a pH of 3.77. So this is just a shortcut for you. I actually solved this with a full ice table as well. And doing the full ice table, I ended up that the pH is equal to 3.78. So like I said, it's going to be very close. It may just be off by 100th or so. But this will save you time. Excuse me. This will save you time whenever you have both the acid and its corresponding base. With Henderson-Hasselbalch equation, so with our ice tables, we always use molarity. With Henderson-Hasselbalch, you can also use the number of moles instead of the molarities. So it would be the same, but you would have at the end plus log of the moles of base divided by moles of acid, but it is still base divided by acid. So using the number of moles instead of molarity is only allowable when you're using the Henderson-Hasselbalch equation. You are not going to be able to plug in moles in an ice table, only in Henderson-Hasselbalch. And remember, whenever we did ice tables and we solved for Ka and Kb, you cannot use moles in Ka and Kb. It has to be molarity. But Henderson-Hasselbalch, you can use moles.